Okay, so a little bit more of section 2.1, we've got net change. Net change, fairly straightforward. As you can see, the definition of net change is right here. It's basically just saying that if you have two values where a is less than b, so kind of picture a number line, a is less than b, then the net change is just finding the function value at b and subtracting the function value at a. So we have an example. We have a function f of x equals 3x squared minus 2. We want the net change for the function from 1 to 3. So for us, that just means you wouldn't have to write this normally, but a equals 1 and b equals 3, since 3 is greater than 1. And then the net change, just bringing it by definition right here, is just finding f of 3 and subtracting f of 1. So if you want, I would go ahead and pause this and see if you can get the answer, and then come back and we will take a look. I'll kind of do it over here. So I'm going to have 3 times 3 squared minus 2. And then I will have 3 times 1 squared minus 2. So that looks like it'll be 27 minus 2, 25. And it'll be 3 minus 2, or 1. And so we can just put that here, 25 minus 1. So our net change here is 24. So the answer to this is just 24. It's just something to remember that that's what the net change is. We'll use it a little bit here in the future, but just remember that it's just f of b minus f of a. Now, a really important thing in this kind of pre-calculus and calculus, and actually, even above, is the idea of domain. Domain is very important, and we're going to look at some functions right now. We're going to talk about the domain and how to kind of figure that out. So you want to remember that by definition, domain is all the permissible inputs. And what that means is it's all the values of x, in this case, looking at these functions. They all use the independent variable x, is that we need to be, when we do this, thinking about what values of x will work, and if there's, more importantly, if there's any values of x that won't work. So there's many functions that have a domain of all real numbers. So for example, let me just maybe give a couple more here. So up at the top, for example, if we have f of x equals 3x plus 4. This is a linear function, which we'll talk about, but the idea here is the domain is any value of x that I can take, multiply by 3, and add 4. Any value of x where I can do that, and out will pop a real number, something that is legit, some real number that we know, is going to work, is going to be part of our domain. And there is no real number that we can't multiply by 3 and add 4 to. There's literally no number out there that's a real number that's not possible for that. So in a case like this, the domain would be all real numbers. So here's set notation, all real numbers. Another quick example, and then we'll move forward. I'll do h of x just to be exciting here. Something like 3x squared plus 2x minus 1. So this is a quadratic function, which we'll talk about, and the same thing is true. Here you're taking a value of x, you're squaring it, you're also multiplying it by 2, and then you're just combining all these numbers. And by doing that, out's going to come a real number. No matter what, you're going to get some real number to come out. And so because of that, again, the domain is all real numbers. But not every function has a domain that's all real numbers. So that's why we have these other examples to take a look at and see what happens. So the first example that we have is f of x equals 1 over x squared minus 4. If you think about it, there's many values of x that you can plug in. You can square that number, you can subtract 4, and then you can do 1 over that number, and out's going to be a real number, out's going to come a real number. Many values of x have this fact, that works. But there may be a couple numbers that don't. So anytime you have a fraction and you're asked to find the domain, so notice this is what's called a rational function, and it has variables in the denominator here. And when we think about something that has a denominator, we need to think about the fact that we can't divide by 0. You cannot divide by 0. So anything that makes your denominator 0 is going to be a problem. So when I see something like this and I'm asked to find the domain, the first thing I think about is what makes the denominator 0. And a good way to figure that out, especially in a case like this where you have x squared minus 4, is to think about factoring it. We've already talked about factoring, so see everything just kind of layers on top of each other. But if we factor this, if we work to factor this, we're going to have x plus 2. Maybe you can think about what the second binomial is going to be. And yeah, we'll have x minus 2. So the idea here is the denominator cannot be 0. And just by looking at these two binomials, we can see that in my first binomial here, if x is negative 2, I'm going to get 0. And I'm going to have 0 in my first binomial. I'm going to have negative 4 in my second binomial. But 0 times anything is 0, and then we end up dividing by 0. So it's telling us right away that negative 2 cannot be part of our domain because it doesn't, the output that comes out is not real. Similarly, in the second binomial, if we plug in 2, you can see that the first binomial will be 4, but the second binomial will be 0, and 4 times 0 is still 0, and 1 divided by 0 is nothing, is not something that can be, it's undefined. So it's telling us, what we're learning from this is that, you know, x squared minus 4 cannot be equal to 0. That's the problem with our domain. And that means that x minus 2 times x plus 2 cannot be equal to 0, which means that x cannot be equal to negative 2 or 2. To write that in set notation, it's pretty much what I just did, but we're saying the set of all x such that x is not equal to negative 2 or 2. So this just tells people it can be anything but those things. And again, just as a side note that you might want to make a note of, anytime you have, maybe I will be say that a little bit differently. You know what, maybe I can just, if you have a fraction, and of course this is like with a function here, but if you have a fraction, you should think denominator cannot be 0. Like that's how you should think about it. And once you think about it that way, hopefully that will help you figure out if there's any values that the denominator can't be. For part B, or letter B here, I do know the difference between letters and numbers. We have a square root function. So square root function. So square root function, what you want to understand is that when we're talking about domain, we're talking about functions. And when we're talking about functions, we're talking about things that are real. So we need real numbers to come out. So although we can take the square root of, say, a negative 4, that's not a real number. So that can't be part of our domain because we wouldn't be able to like graph that on a Cartesian plane. So when we think about the square root function, the important thing to remember is that the inside needs to be greater than or equal to 0. That's really all you have to remember. And so then to think about the domain, you just take the inside and you think about what values make it greater than or equal to 0, and you just solve this inequality here, and that will tell you everything you need to know. So the thing to be careful of course, is if I solve this for x, I need to, as you might be able to see, switch my inequality because we're dividing by a negative. But if you think about all the values of x here, so this is telling us x needs to be less than or equal to 5. That makes sense because you can see just from the inside of your square root, if x is bigger than 5, say x is 10, for example, 10 cannot be part of our domain because 5 minus 10 is negative 5, and then we're taking the square root of negative 5. However, if we pick values that are less than or equal to 5, if I pick 5, I get the square root of 0. That's fine. That's 0. If I pick x is equal to 4, 5 minus 4 is 1, square root of 1 is 1. I'm good. And so that's why this is our domain, x being less than or equal to 5, because anything that is less than or equal to 5, whether it be 4.5, whether it be negative 0.15782, it's going to give us a positive number underneath the square root sign, and then the square root of that is still a real number. So it's part of our domain. So the way we write that is just all x, the set of all x, such that x is less than or equal to 5. So that's all you have to do. And now we kind of combine the two in part C here. So in looking at C, you see, well, you got a fraction and you got a square root. So we already know that inside the square root needs to be greater than or equal to 0, greater than or equal to 0. But now it's in a denominator as well. So it kind of, again, combines these two things. If you have something in a denominator, it cannot be equal to 0. You cannot give any value where it's equal to 0. But because it's a square root, we also need it to be greater than 0. So putting those two things together, we've got square root in denominator, okay? So in this case, the inside still needs to be greater than or equal to 0, but it can't be 0 because we've got it in a denominator. So all that this means is that we just need to take the inside of this square root and we're going to make it greater than 0 and figure out what values make that true. It's very straightforward now. So this has to be true. As long as the inside is greater than 0, you're going to have a positive number in your root. You're going to be able to take the square root of it. It's going to be something real. It might not be pretty. It might be irrational. That's okay. That's still a real number. 1 divided by that, still real. Still a real number. So x is greater than 3. And that's it. I mean, I'm going to put it in my set notation, but that's all you have to do. So it's the things to think about there. You cannot put anything in for x that's not going to give you something real. So that's what you have to focus on. And then the last one here is D, and that's j of x, exciting j of x here. And it is the cube root. So cube root mixes things up a little bit because you can take, so here's what to think about with a cube root. If I were to say, what is the cube root of -8, for example? So let's say x is 0. If I were to say, find j of 0, you'd say, oh, that's the cube root of -8. But the cube root of -8 is saying, is there a number that if you multiply it times itself 3 times something times something times something, do you get -8? Is there such a number? That's what that's saying, cube root of -8. And you know that a negative times a negative times a negative is a negative. So there is going to be such a number. So -2 times -2 is 4, but times -2 is -8. And so because of that, it tells us that we could put in 0. 0 is part of our domain. And more importantly, what it means is that you can put in anything even less than 0. You could put in anything that's less than 8, and you're going to be taking the cube root of a negative, but that's okay, because a negative times a negative times a negative is still negative. Conversely, if you put in something like, if we put in x being 16, now x being 16 gives us the cube root of 8, because 16 minus 8 is 8. So the cube root of 8, is there a number that you multiply times itself 3 times and you get 8? Yeah, it's 2. So you can also look at positive numbers and take the cube root of those. All of this is to say that with cube roots, the inside can be positive or negative. Positive or negative. And that's great because it really means that the inside can be anything. And you can still find a real number. A real number is still going to come out. Again, it might be rational, it might be irrational, but it's still real. So what that means is that here is another example of a function who has a domain of all real numbers, our cube root functions. And we'll see this a bit more in the future in the later sections, but when you look at the graph of this, you will notice that the domain is all real numbers. And you'll notice on the graphs of these other functions, A, B, and C at least, that the domain is not. And then we can see that graphically as well and hopefully put it all together and have it make sense.